just discussing about the previous class. Wait a minute, wait a minute, wait a minute. Okay. So whether my PDF is visible for you people?
Yes, sir.
So in the last class, we were discussing about the small signal model of the MOSFET. So in which we have seen what is the amount of what is how we are going to consider the small signal approximation. So we know that MOSFET for a MOSFET the voltage is the input signal which you are going to apply between the gate and source. For this we have considered a common source configuration, right? So in common source configuration, source will be a common between the input side as well as output side, and then for the gate and source, I'm just applying a gate to source voltage. So for that, in order to make the MOSFET, and along with that, at the drain terminal, we are going to apply a drain resistance through which the drain current ID will be flowing, and across the drain to source voltage is nothing but output voltage from which you are going to get the input voltage amplified version of the input voltage will be getting across the drain to source voltage. So now if we consider the gate to source voltage, so first thing is that we need to make the MOSFET to bias to an operating point such a way that you will be getting a maximum amplification, and we also know that the MOSFET will be for amplification purpose we are going to bias the MOSFET. MOSFET has to be biased to in saturation region. So in order to make the MOSFET to operate in saturation, what is the conditions required? So that is the conditions required is nothing but so the drain to source voltage must be equal to or greater than drain to source voltage. So that is the first second condition. So for the in order to turn on the MOSFET, first we need to apply gate to source voltage should be greater than threshold voltage. So VGS will be should be must be greater than threshold voltage. So that is the common requirement for making use of any MOSFET. So if the gate voltage is greater than the threshold voltage, then obviously your MOSFET will be in on state. So that means the channel will be established between the drain and source. So in order to establish a channel, establish a current and to make the MOSFET to operate in saturation, so we need to bias the we need to make the drain to source voltage must be greater than VGS minus VT, or it should be greater than over drain voltage. So whenever the drain to source voltage is equal to or greater than VGS minus VT, then the device is going to be operated in saturation. So in saturation region, when it is going to operate, so we need to properly bias such a way that you will be getting the maximum amplification. So for that, after getting the MOSFET operating bias in Q point such a way that you will get maximum amplification, so you will be connecting the small signal. So small signal VGS, so that small signal will be connected with respect to the bias and gate to source voltage. So that you will be getting instantaneous value of the gate to source voltage across between the gate and source. Since instantaneous value that is because of the gate to source voltage is the sum of the small signal as well as the DC gate to source voltage. So you will be getting the voltage also going to be time varying input voltage. So you will be getting if I want to know what is the perfect voltage at that instant, means that is going to be given by this instantaneous value gate to source voltage. So this is nothing but a instantaneous gate to source voltage. So now instantaneous gate voltage means you will be getting the output also, all the terminal currents as well as the terminal voltages will be referred with respect to instantaneous value. So the drain to source current ID as well as the output drain to source voltage. So all the terms you can see observe here, all are nothing but instantaneous value. So once the instantaneous value has been done, so then we need to find out what is the contribution of the small signal current. So signal current is nothing but because of the small signal which has been added in series with respect to uh, small signal. So because of applying this small signal, wait a minute, some of you are not muted yourself. Kindly mute yourself. Okay. So the small signal current in the drain terminal. So if we look at this small signal current in the drain terminal means there is nothing but what is the contribution of this small signal? That means on applying the small signal voltage VGS across the input side. So the output current is also going to change. That is what you're going to have. That is nothing but signal current in the drain terminal. So in order to find out that the signal current, that is what is the percentage change or what is the change in the drain current, so we need to find out what is the instantaneous gate to source voltage. So first we need to know, because gate to source voltage is the input side, wherein which on application of this gate to source voltage, so you will be getting the maximum output voltage. So VGS is nothing but an instantaneous gate value. So this is the sum of the DC gate to source voltage and AC, that is the signal gate to source voltage. So this is the nothing but so this is DC gate voltage. Because of the DC biasing conditions, so we are going to make the MOSFET to operate in saturation region with respect to gate to source voltage DC, and then small signal is nothing but this one. So we need to know what is meant by small signal. For that we are going to obtain what is the signal drain to source current. So total in the input voltage across the gate to source is nothing but instantaneous gate to source. So for which you are going to get the instantaneous drain current. So that is going to be flowing between the drain and source of the MOSFET. So ID is nothing but instantaneous drain current. So this instantaneous drain current will be equal to, so you have to write saturated current equation, because in this we are going to assume that drain to source voltage is greater than VGS minus VT, that is greater than overdrive voltage. So for that we are going to substitute the expression for saturation current expression. So this is the saturated current expression. So that is a half Kn dash into gain into VGS minus VT whole square. So this VGS minus VT whole square, in place of VGS we are going to have instantaneous value. Since we are going to have instantaneous current, so the value of this entire thing is the remote instantaneous value of the gate to source voltage VGS minus VT. So that VGS is the instantaneous value. So for that we are going to substitute the DC gate to source plus signal source to gate to source voltage minus VT whole square. So this I can write, so that is a plus b whole square. So a plus b whole square. So VGS minus VT, all the DC source can be considered as a A, and the small signal source gate to source voltage is considered as a B. So we can have is summed as VGS minus VT. So a plus b whole square. So a plus b whole square is nothing but a square plus 2ab plus b square. So the same thing here we're going to write. So half into kn is a common, and in place of this you are going to write a square. A square is nothing but VGS minus VT whole square, that is a square plus 2ab. So 2 gets cancelled. This half kn into 2ab. So 2 gets cancelled, and write down the corresponding a and b term. So VGS minus VT into VGS, and then so we are going to write the b square term. So b term b square. So half a kn is common and VGS square. So in this current drain to source current equation, you can see in this expression. So first term is a DC drain current, right? So this is nothing but current that is going to flow between the MOSFET because of the DC source only. So DC source. So VGS is gate to source voltage because of the DC gate to source voltage. The current flowing is nothing but ID. So that is, you can imagine. Okay, so that is nothing but only DC source. And whereas in the second and third term, you can see there is a signal component associated with it. So one is a signal directly proportional to VGS, that is proportional. So another term is it is square of the gate to source voltage. So with this you can say this is a kn into VGS minus VT into VGS plus a half into kn into VGS square. So this is two terms we are going to. So in this which is going to have contribution, so which we are going to see now right now. So we need to say is that these two components are there. So half kn into VGS square. So we know that already. So we are going to take the gate to source voltage as a small gate to source voltage. So whenever it is going to be a square of the small signal voltage, then obviously the resulting equation will be having a very small value. So we need to we can say that this is going to be very less when compared to this value. So kn into VGS minus VT into VGS. So this is nothing but expression. So here we're going to obtain the relation between the how much the small signal gate to source voltage must be. So that we're going to do an approximation for small gate to source voltage. So here in this we're going to obtain the relation. So VGS should be very less than 2 times of VGS minus VT. So these two VGS will get cancelled, and we are going to obtain the gate to source voltage must be very smaller compared to 2 times twice the gate to gate to source voltage, effective gate to source voltage, or twice the old drive voltage. So that you can write here. So if this is satisfied, so if it is VGS is less than 2 times of water voltage, then we can call it as this as a small signal condition. So this has to be satisfied, then only we can write the drain to source current. Instantaneous drain to source current will be equal to DC drain current plus ID, that is a small signal current. So that small signal current, we are going to get this as an expression. So Kn into Vgs minus Vt into Vgs. So because this term you are going to neglect because it is going to be very small, so only these two condition is going to be contributed. So Kn into Vgs minus Vt into Vgs. So this is the signal current. So this is the nothing but a signal current. So in this we can also obtain a relation, because here in the right hand side we are going to have small signal gate to source voltage, and you can see the output current is denoted with a small signal current ID. So this gives an relation, so that is given for a MOSFET. So that is the bottom. So output current to input gate to source voltage, that is the whatever the value is there, so that value can be considered as what? So that can be considered as a transconductance. So that is a MOSFET transconductance GM. So GM can be written as a ratio of output drain to source voltage to gate to source voltage. This is nothing but a signal drain to source current, and VGS is nothing but a gate to source voltage, which will be equal to Kn times of VGS minus Vt. So this is entire thing is nothing but a transconductance, and we can write in terms of ordinary voltage as well. So Kn into ordinary voltage. So this is nothing but another expression that is going to have for the transconductance GM. So this same thing we can see in the graphical representation as well. So how it is going to obtain the transconductance for a given relation. So this is nothing but IV characteristics, in which output y-axis is nothing but a drain current, and x-axis is nothing but a instantaneous value of the gate to source voltage. And we also know that in the x-axis whenever the input gate to source voltage, so x-axis is nothing but gate to source voltage. So whenever the gate to source voltage is greater than Vt, then only the current is going to increase in exponential way. So you can see this is the for increase in the gate to source voltage, you can see there is increase in the current. And we also know that for a given gate to source voltage, that is for in given this point, at this point we are going to select DC gate to source voltage, so that it is going to operate at operate with the specific quiescent point. So this point you are going to select, so that you will be getting a maximum swing. So that we are going to select this point as a for which you will be getting the gate to source voltage as this, and at this point what is the current that is flowing is nothing but a DC drain current ID. So this is nothing but a biasing of this with the DC biasing point. Once this DC biasing point has been done, so then next is what? So you're going to add a small signal VGS. Small signal VGS is nothing but this is the small signal VGS. So that means you're going to vary. You're going to consider on the small signal, and which is a time varying signal, so which is going to vary this operating Q point, so that it is going to move the Q point to shift above as well as below like this. So that is the time varying signal for which you are going to get instantaneous gate to source voltage to lie within these two. So instantaneous value of the gate to source voltage is going to lie, so positive peak over here and a negative peak over here. So that if you plot so if you obtain this one, so for which you will be getting the output drain current as this. This is the signal current. So this is a small signal voltage for which you are going to change. You are going to get output current. So which is going to change. That is being given by like this. So this is the ID signal current, and this is nothing but signal gate to source voltage. So small signal gate to source voltage, and this point and this point. So this is nothing but a VGS point, and this point is nothing but a VT point. So the difference between these two, VGS minus VT, so this point is called as the overdrive voltage. So you have to note on all the important parameters with respect to the MOSFET, and so this is nothing but overdrive voltage, and this is nothing but a quiescent point, and that point what is the gate to source voltage, and this point what is the drain current, and you're going to see. And if you plot a slope, so this is the output current is going to vary. So that is ID is going to vary between these peaks. And if you plot a straight line, so how it is going to time varying signal. So if you plot a straight line, so you will get with respect to input and output. So this is the slope that is given to be given by the transconductance GM. So that slope is almost a linear segment if you consider. So it will be almost linear segment. You can see the straight line. So that is going to connect between this point and this point. So it is going to change from this Q point is going to vary from this point, and for which you are going to get the drain current to vary. So that point is called as a transconductance. This slope is nothing but a transconductance, and it is almost linear. So now we are going to find out what is the gain associated with for this MOSFET. So this is the gain voltage gain. So when we are going to see the circuit again, so we are going to find out what is the output voltage. So that output voltage is given by drain to source voltage VDS. So that is equal to VDD minus ID into RD. So this is the instantaneous drain to source voltage. VDD is the drain to power supply voltage VDD minus RD into ID. So this ID is nothing but instantaneous drain current. So whatever you have found out what is the instantaneous drain current. So that
Sir,
hello,
sir, PDF is not visible, sir.
PDF is not visible.
Yes, sir.
Wait a minute. Whether it is visible now.
Yes, sir. Now it is visible.
Okay. So in
Okay.
this ID VGS characteristics, you can see along the x-axis is nothing but a gate to source voltage, and along the y-axis it is the drain to source current. Okay. So y-axis, this is the instantaneous value of the drain current, and this is nothing but a DC drain current. So you have to be very careful. So this is the y-axis is going to, that means the gate source voltage is going to increase from 0 to maximum value. So in that we are going to select this point as a gate to source voltage, so that you will be getting operating the MOSFET with the Q point. So at this corresponding to Q point, to make the MOSFET to operate in saturation region, so you are going to make this as a Q point, such a way that you will be getting the maximum amplification without any losing of the information. That is input or output voltage swing during the output voltage swing, so you will be not losing any during the positive or negative peak. So that this point is going to select, and that corresponding point you can see this is nothing but IV VD characteristic. So that this point is called as a drain current, which is going to, that is nothing but a DC drain current. And when you and you plot the same thing in backward, so you can see this is the Q point along the x-axis. You will be getting this point, so that point of voltage is called as a DC gate to source voltage. So this is a DC gate to source voltage, and this is a DC drain current. So when you are going to have this DC gate to source voltage as well as a DC drain current, so you can see for a small signal, we are going to give as an input along with the DC drain gate to source voltage. So at the input side, you're going to give a time varying signal. So you can see this is a small signal, that is a VGS. So that is nothing but a small letter V with JS, that is nothing but a signal gate to source voltage, which is going to be time varying signal. So when you are going to give a time varying signal, you can also see that there is a fluctuation of the Q point. It is going to move up as well as down. So that means you will be having Q point is also going to vary. So at the same time, you can see the output is also, drain current is also, since the gate to source voltage is going to vary, so obviously the drain to source current, so drain current, which is a parameter of, which is a function of this gate to source voltage, so this is also going to vary. So this is going to vary with respect to this because of the DC, because of the signal gate to source voltage. So because of this signal gate to source voltage, the signal current is going to vary. So this is nothing but a signal current, and this is nothing but a signal gate to source voltage, and this is nothing but a DC gate to source voltage. And with respect to DC gate voltage and this threshold voltage, you can see the difference. So that is nothing but a overdrain voltage, that is VGS minus VT. This is nothing but a voltage DC, that is overdrain voltage, or you can also call it as a effective gate to source voltage, VGS minus VT. And then when you can see here, this is the Q point is going to move up and down. So we can say that there is a relation between the drain current as well as the input gate to source voltage, so that you can plot the slope. That is, the slope is nothing but the transconductance slope, that is given by GM. So it is going to be called it as GM. So this is the small signal operation of the MOSFET amplifier. Okay, so after this we are going to see what is the voltage gain. So in order to find out the voltage gain, we need to know what is the output voltage. So returning to the back to the same circuit as shown in the figure. So in this figure, so you can see the output voltage is nothing but what? So drain to source voltage. So this drain to source voltage is equal to what? So this is the instantaneous value of the drain to source voltage, which is equal to VDD minus ID into RD. So that gives the instantaneous value of the drain to source voltage. The same thing we are going to write over here. So VDS will be equal to VDD minus RD into ID. So this is the important instantaneous value of the drain current, and this is the power supply voltage VDD minus RD into ID. So this gives the instantaneous value of the drain to source voltage. So instantaneous value of the drain to source voltage has been written. So you can expand the term. So VDD minus RD into So this instantaneous value can be written as what? So DC drain current plus signal current, drain current, because now the current ID as well as small signal current ID also we know. So we can substitute the value of the signal drain current over here. So now we can write VDS will be equal to VDD minus ID into RD as one expression, as well as VDD minus RD into small rd into id as another expression. So VDD minus RD into id, I can write it as capital drain to source voltage, that is DC drain to source voltage, minus ID into RD. So this ID is nothing but a signal current, and this is the signal, there is the drain resistance RD. So this is nothing but a output voltage. So that is the output voltage is 180 degree out of phase, because of which the signal current, you can see there is a 180 degree out of phase. So minus RD into ID. So minus ID into RD, I can write it as the signal. This I can write. So now we can write the substitute the term. So this is nothing but instantaneous drain to source voltage. This will be equal to sum of the drain to source voltage plus signal drain to source voltage. So this is can be written as signal drain to source voltage. So what is the what VDS will be? So this is signal drain to source voltage will be equal to minus ID into RD, and I can write ID as GM into VGS, because we are going to find out the voltage gain. So I should have something which should be equal to input. In terms of input voltage, we can write so minus GM into VGS. So this VGS is nothing but input, and this the VDS is nothing but output. So ratio of VDS to input voltage, so that gives the gain AV. So this is nothing but voltage gain AV. So AV will be equal to VDS by VGS, which will be equal to minus GM times of RD. So this is a gain equation for the common source amplifier. So after that we have seen the DC, separating the DC and signal analysis. In this separating the DC analysis and the signal analysis, so we are going to remove the DC content, and we are going to apply only generating a model which is going to function for FET. So how it is going to be replaced with the FET? So with the DC small signal operation. For this small signal operation, first we are going to write all the three terminals, so gate, source as well as drain, as like this, because we are going to have a common input as a source, so we can have source to be written as the common between the input, and so we are going to write it at the below, and the gate at the input. So VGS is the input side, gate to source voltage, and for which the output current will be equal to GM times of VGS. So this is nothing but the output current. So wait a minute, I will just come back in a minute. So wait a minute. Okay, so I was discussing about the small signal model. So in the small signal operation model, so first we are going to develop a model, so which will be working with respect to the small signal. So here we are going to have only in terms of small signal only. So gate, source as well as drain. So source is a common between the input side as well as output side. So we are going to write the source at the below, and gate at the left side, and the right side it will be drain. So since there is no resistance, that means the gate current is zero. That means between the gate and source, the current flowing is zero. So there will be no resistance associated with across the input side, because of which you can say that because of which we can say that the input side of the common source amplifier is having the infinite input impedance. So because of which we can say the small signal current can be established between the gate and source, that is the VGS, small signal VGS, and for which it is going to obtain a current that is going to flow between the drain and source, that is the ID, that is the signal current ID. So ID can be written in terms of a controlled current source, that is the controlled voltage source. So here is a output is nothing but a current which is going to be controlled by the input signal voltage VGS. So you are going to have a voltage controlled voltage source, so it is represented as GM times of VGS. So this is about the voltage controlled voltage device, so voltage controlled current device, so voltage controlled current source. And the same thing as I told in the previous class. So in the MOSFET, whenever it is going to operate in saturation region, so we can say that for secondary effects and all. So when you're going to realize the MOSFET at deep micron as well as submicron level, so the equations of the saturation equation is not going to hold good. So for submicron levels, 180 nanometer technology or 0.45 nanometer technology, so that is nothing but whenever the MOSFET fabrication are going to be scaling down. So scaling down in the sense when the device size is going to be shrinking. So when you are going to reduce the size of the MOSFET, so whatever the equations or the equations which will be holds good, it will be holds good for only the channel length above 1 micrometer. So whenever you are going to reduce the MOSFET size less than 1 micrometer, then this equation, so that is saturated current equation, is not going to hold good. And instead of the current being constant in the saturation region, so what will happen? So in the constant being saturation region, so ID will be independent of VDS term ಅಂತ ಹೇಳ್ತಾರೆ. That means drain to source voltage ಮೇಲೆ it is not going to depend. It will be depending only on half Kn dash W by L, half Kn dash W by L into VGS minus VT whole square. So that is the current expression for saturated current expression for drain to source. That will be holds good only for the channel length greater than 1 micrometer. So if it is less than 1 micrometer means then obviously instead of being the current ID is independent on VDS, so it is going to be dependent, because we can see in the deep submicron and level and also there is as you increase the drain to source voltage greater than old ray voltage, so you can see there is a increase in the current as well. So for that we cannot say that current is independent of VDS term. It is depending upon VDS term, because when you look at the VI characteristic, so you can say that you can find the slope. So as you increase the drain to source voltage, you can also see there is a small increase in the drain to source current. This is nothing but instead of being constant in the saturation, you are going to get a certain slope. That means we increase, so we are going to model the current expression with the new expression that is going to involving, so half Kn into W by L VGS minus VT whole square into 1 plus lambda into VDS. That means lambda is nothing but a channel length modulation. So along with that VDS term, so as you see that the VDS is going to be dependent, so in the IDS is going to be dependent on VDS term. So we can model for the device which is going to have a less than 1 micrometer, so that you are going to have a channel length modulation effect. So that channel length modulation effect, in order to overcome that, so you are going to have a in order to reduce that channel length modulation effect, so we are going to model the small signal model with the finite amount of resistance R naught to be connected between drain and source. So this finite amount of resistance, output resistance R naught is going to has been generated because between the drain and source voltage. So as you increase the drain and source voltage, you can see there is the current is also going to increase. So that is going to be modeled as a finite amount of drain to source resistance. So this is nothing but the R naught. So these models works with both NMOS as well as PMOS transistors properly. And for drain to source resistance is going to be modeled by using this expression. R naught is equal to VA by ID. So there is the early voltage and ID. So there is the current. So if you plot the VI characteristics of back, you will be getting certain voltage across the negative x-axis, that is going to be considered as the early voltage. So that early voltage point, so you can get the constant current. So R naught will be the value, that is the output resistance. So VA by ID. So here VA written modular symbol, because the voltage which you are going to get VA will be in the terms of negative voltage. So divided by ID. So this is going to give us a R naught. So and then we can also find out what is the drain to source condition. So it is also going to consider as the early voltage will be equal to 1 over lambda. That is the channel length modulation parameter, and it is going to be depend upon the type of the process technology. So what type of technology so you are going to use. So either you are going to use 180 nanometer, 0.45 nanometer, or submicron levels, or else micron level. So depending upon the type of the process technology that we are going to do fabricate the MOSFET. So depending upon that, you are going to consider this is going to work with respect to the channel length. Okay. So the proportional. So it is going to proportional. The channel length is going to proportional with respect to the MOSFET channel length. So early voltage is proportional to MOSFET channel length, and then so we can write the expression for this in terms of overdrive voltage. And typically the values of the resistance R naught is going to lie with the 10 km to 1000 kilo ohms. That means typically the value is a very larger value. So you can say that this is going to be very large whenever it is going to connect with the drain resistance, which will be also in terms of kilo ohms. So from parallel combination of these two resistors is going to reduce the gain source. So now the gain which has been obtained in the previous session for the small signal gain, so that is the drain to source voltage over VGS, that is the ratio of VDS to VGS, which will be equal to minus GM into RD parallel RL. R naught. So RD parallel R naught. So R finite amount of resistance is going to reduce the gain. So hence we can say that including R naught is going to reduce the gain expression. So this is about the small signal voltage gain. So once the small signal voltage gain is done, so next we are going to move. The next topic is the transconductance, the value of the transconductance. So we have already found out what you mean by transconductance. So in this we are going to obtain the different relations. That means how you are going to find out the different expressions for transconductance you are going to learn in this one. So we shall now take a look further look at the MOSFET transconductance, which can be written as, so GM can be written as what? GM can be written as what? Kn into W by L VGS minus VT. So that is the expression, right? So Kn dash into W by L. So Kn dash is equal to what? Mu n COX W by L. So mu n into COX. So also you can write transconductance can be written as Kn dash into W by L VGS minus VT. So this is the normal expression of the transconductance. So this expression I can write in terms of overdrive voltage. So this is one of the relation that is going to give relationship between the transconductance. So as well as the transconductance. So GM can be written as what? So entire thing K and dash I can write W by L VGS minus VT, I can write it as overdrive voltage. So this is one expression. So which we have got in the previous expression. So equation 7.32. So if you look at the equation 7.32, that is the equation for the transconductance, right? So GM is equal to what? Kn into VGS minus VT. So Kn into VGS minus VT means Kn dash into W by L VGS minus VT enter. So that is the same expression going to rewrite over here. But in place of VGS minus VT, we are going to write overdrive voltage. So this is another expression how you can write for the transconductance. So in this expression, so we can say that GM, so that is the transconductance is proportional to Kn dash. So Kn dash means what? Mu n into COX. So that is depend upon the process gain parameter. So Kn dash is nothing but the process gain parameter. So process dependent parameter. Sorry. So process dependent parameter, that is mu n into COX. So that is depend upon the Kn dash as well as the W by L ratio. It is dependent upon directly proportional to Kn dash as well as the W by L ratio of the transistor. Hence, to obtain a relatively large transconductance, the device must be short and wide. So what should be the length of the channel? So length should be very small, width should be very high. So then only you will be getting this GM transconductance value to be very large. So this is for a given device is a constant, so we cannot able to alter this mu n into COX for a given MOSFET, and so only plausibility is that with respect to channel length and width. So if I want to increase the transconductance gain, so the GM value I should increase means only one way, that is because so I can reduce the length. So length of the MOSFET can be reduced, and the width of the MOSFET can be increased. So width, if you are going to increase, and length you are going to reduce, means the gain transconductance is going to increase only. Hence, to obtain large transconductance, the transconductance device must be short and wide. And also from that given device transconductance is proportional to overdrive voltage, so it is also proportional to overdrive voltage, so VGS minus VT. So however the gate to source voltage increase ಮಾಡ್ದಂಗೆ, so transconductance is also going to increase the same thing. So increasing the GM by biasing the device at a larger gate to source voltage has the disadvantage of reducing the allowable signal swing at the drain. So one thing important is that so signal gate to source voltage increase ಮಾಡಿದಷ್ಟು, so you will be getting the transconductance is going to increase, but at the same time this gate to source voltage cannot be increased up to a certain limit. So if you increase still if you are going to increase beyond the limit means the output in the output the signal swing is going to reduce. So that means the portion of the signal is going to getting clipped off. So there is limit of reducing increasing the value of the gate to source voltage. So another useful expression for transconductance can be obtained by substituting the VOV in the equation 7.4 by this equation. So how you are going to get this expression? So VOV will be equal to what? So overdrive voltage. So this expression has been obtained from drain to source current expression. Okay. So drain to source current expression so ID will be equal to what? So ID will be equal to half kn into VOV whole square ಅಂತ ಬಂದಿದೆ. So equation 7.38 ಅಲ್ಲಿ, so we know that I can represent VOV in terms of ID. So overdrive voltage ಅಂದ್ರೆ ಏನು? So overdrive voltage means I can write VOV will be equal to 2 times of ID, so okay, divided by kn. So the same thing here we are going to write over here. So 2 times of ID divided by kn dash into w by l. So that is for the current expression. So kn dash into w by l. So kn can be written as what? So kn dash w by l into VOV whole square. So VOV whole square can be written as what? 2 times of ID divided by kn dash w by l. So the same thing here is written. So in place of VOV, so in this expression, so 7.40. So what here written is the same expression 7.40 ತಗೊಂಡು. So VOV can be written as what? Square root of 2 ID. Okay, so square root of 2 ID and then divided by kn dash into w by l. So kn dash into w by l square root is there. So here it is what? So kn dash w by l is there. So this can be written as square root into square root, right? So square root of kn dash w by l into square root of kn dash w by l whole square ಮಾಡಿದ್ರೆ, so you will be getting kn dash w by l. So 1 square root of kn dash w by l will get cancelled with the denominator term and left out with what? So square root of 2 ID. So square root of kn dash w by l. So the same thing here we are going to write square root of 2 ID square root of kn dash w by l. So this is the another expression. So by substituting the value for VOV. So when you substitute the value of VOV with respect to the current drain to source current expression, I can write the same transconductance with which is going to deals with the square root of the DC bias current. So here we can see this is nothing but a DC bias current and it is proportional to square root of W by L. So for a given transconductance. So this is about the another expression which you can write. So these are all important things. So in the exam they have asked in the what are the different alternative ways of writing the transconductance expression they have asked. So you have to start with the normal general expression and you have to represent with respect to overdrive voltage. Hello, mute ಮಾಡ್ಕೊಳ್ರಾ. Okay. So how we are going to start? So start with the normal transconductance expression. So K dash W by L into VOV. So you are going to start. After that you are going to substitute the value of VOV. So E VOV ಎಲ್ಲಿಂದ find out ಮಾಡ್ತೀರಾ? ಇಲ್ಲಿ drain to source current ಇರುತ್ತಲ್ಲ. So from that drain to source current you are going to find out the value and you are going to substitute the value and you will be getting the another expression which is going to support the transconductance expression. So Gm will be equal to square root of 2 K dash W by L square root of ID. So from this expression also we can say that for a given MOSFET, so transconductance is proportional to what? Square root of DC bias current. So ID is DC bias current as well as square root of W by L ratio. So it is also relating. So it is directly proportional to square root of width and length ratio. So we'll be shortly discussing about the transconductance of bipolar junction is proportional to bias current. So in that in the previous BJT discuss ಮಾಡ್ಬೇಕಾದ್ರೆ, so GM was directly proportional to IC by VT. So that means that is the expression for the BJT. So GM will be equal to what? So IC by VT. So IC is the remote signal current, that is the DC output collector current. So BJT, so it was directly proportional to DC drain current, whereas in this DC current, DC bias current, and it was independent of the physical size and the geometry. So physical size and the geometry will depend on that. That means physical size and it was not depending upon the process dependent parameter as well as the geometry dependent parameter. Like how it is going to depend in this case, MOSFET process dependent parameter ಮೇಲೂ ಡಿಪೆಂಡ್ ಆಗ್ತಾ ಇದೆ, geometry dependent factor, that is channel width ಮತ್ತು channel length along with the channel mobility along with the channel threshold voltage. All these things are nothing but a process dependent parameter, and geometry dependent factor ಮೇಲೂ ಡಿಪೆಂಡ್ ಆಗ್ತಾ So along with the square root of the ID, whereas there it was directly proportional to bias current and it was independent of physical size and geometry. So you have to remember, recall that. So for that value, so to gain some insight into the value of transconductance in MOSFET, so consider one example for a problem we are going to solve. Consider an IC developing IC integrated circuit device operating at ID is equal to 0.5 milliamps. So we're going to see that for a given device of MOSFET, so the drain current is 0.5 milliamps and having the Kn dash, that is the Kn dash is nothing but what mu n COX W by L. So entire thing I'm going to write it as 120 microamps per volt square. So it is n, and using the equation 7.41, so it shows that W by L is equal to 1. So Gm is equal to 0.35 milliamp per volt, where a device for which W by L is equal to 100 has to 3.5 milliamp per volt. So that means if I want to know Kn dash, it is 120 microamp per volt square. If you substitute over here, ID is equal to what? So ID is equal to 0.5 milliamps substitute more. So I can find out where a device for which W by L is 100, W by L is equal to 100 and the. So you'll be getting this transconductance value as 3.5 milliamp per volt. So this is the expression for the given device characteristics for the MOSFET. So for which we are going to get the transconductance value as 3.5 milliamp per volt. So in contrast, so this is the value of the transconductance. So in the previous expression we have told right. So how the transconductance of the BJT will be greater than that of the transconductance of the MOSFET. So for that we are going to give the illustration for how the transconductance is going to be for the MOSFET, for the BJT is greater than the MOSFET. In contrast, BJT operating at a collector current 0.5 milliamp ಆಯ್ತು ಅಂದ್ರೆ, so the collector current 0.5 milliamp, the transconductance will be equal to what? 20 milliamp per volt. So you can see what is the difference you are going to get. So GM 3.5 milliamp per volt is where, and 20 milliamp per volt is where. So it is obviously 5 times greater than this one. So approximately if you consider this as a 4 milliamp per volt, so it is 20 milliamp per volt you are going to get as a transconductance for this one. So this is an expression. So through that you can say that transconductance of BJT is very much greater than that transconductance of that you are going to get of MOSFET, because it is going to depend on the process as well as the geometry. So for the MOSFET, so that is what you're going to. Whereas in the BJT it is depend only on the only on the only on the DC collector current IC. So DC collector current, that is IC divided by VT. So IC is equal to 0.5 milliamps and divided by VT is equal to 25 millivolts and ankonಡ್ರೆ. So you will be getting what? So you will be getting the obviously 20 milliamp per volt. So that is the transconductance which is having higher when compared to that of transconductance of MOSFET. So another expression which can be written for the transconductance. So this is the second expression for transconductance, and now we can write the transconductance for the third expression. So Gm can be written in terms of will be equal to 2ID divided by Vgs minus Vt. How I can write the Gm is so by using the substituting the value of Kn dash W by L. So ಇಲ್ಲಿ ಏನು ಮಾಡಿದೆ ಫಸ್ಟ್ VGS minus VT I can substitute as VOV ಅಂತ ಬರಲಿ. So for this VOV I am substituted the drain current. Now I am going to substitute the Kn dash W by L. So now I am going to substitute Kn dash W by L current expression ಏನಿತ್ತಲ್ವಾ. So this one you can see again. So Kn dash W by L I am going to substitute for this equation. So 2ID divided by VGS minus VT. So 2ID divided by VGS minus VT whole square, that I am going to substitute over here. So now 2ID divided by VGS minus VT, that is nothing but a voltage that I am going to substitute over here. So transconductance GM can be written as what? So transconductance GM is given by this. So Kn dash W by L VGS minus VT. So now I can substitute the value of this with what? So 2ID divided by VGS minus VT whole square and the other. So VGS minus VT whole square and this VGS minus VT gets cancelled. So left out with the transconductance expression as what? 2ID divided by VGS minus VT. So that is what you are going to get over here. So 2ID divided by VGS minus VT, or you can write 2ID divided by VOV. So these are the three different expressions for transconductance. So this has been asked for 6 to 8 marks. Okay. So we have to write the expression for transconductance, and they are going to ask what is the value for what are the alternate expressions. So first you are going to write the general expression, and k and dash w by L VGS minus VT. VGS minus VT I'm going to substitute as VOV, first expression. And then in the second, for the second alternative expression for transconductance, for VOV I'm going to substitute with the current expression, so that I'm going to get the new expression for transconductance, which is nothing but square root of ID, square root of W by L, square root of 2 k and dash. So this is the second alternative. So now for the third expression to get, so I'm going to retain VOV as it is, and I'm going to substitute k and dash W by L with the current expression. So k and dash W by L can be written as what? 2IDA divided by VGS minus VT whole square. 2IDA divided by VGS minus VT whole square into VGS minus VT. So 1 VGS minus VT, 1 VGS minus VT get cancelled. So left out with this term. So 2IDA divided by VGS minus VT, which will be equal to 2IDA divided by overdrive voltage. In terms of overdrive voltage, I am going to write. So these three alternative expression you have to write for the different alternative expression for transconductance. So whether people are understanding or what? Hello, whether people are understanding or what? With this, just completed the module 1. So whether you are having any doubts with module 1? Hello, whether you are having any doubts?
Sir.
Whether you are having any doubts? Module 1 has been completed now. So from the beginning till this transconductance, so your portion is there. Okay, so this is the entire thing is the module 1. So BJT as well as MOSFET we have done. So small signal operation of BJT as well as small signal operation of MOSFET we have done, and the last topic was transconductance parameter. Okay, with this just concluded the first module. If you are any having doubts, you can discuss. And I just posted 2 model question papers in your group. So kindly go through first question, so which will be from the both the question paper you can see, and if you come across any doubt you can ask me. Okay. Okay, with this I'll just conclude today's session. We'll meet you tomorrow. Bye.
Thank you, sir.
Thank you.